Algebras. Welcome to your Chapter 5, Lesson 8 notes. This is the end of Chapter 5 with this one, so let's get into this. This is actually, I love this part of this lesson, this part of this chapter. I got a phone call when I was first starting teaching from my BFF in college, and her boyfriend at the time, now husband, called me to ask me to go through systems of linear inequalities with him because he had to create a chart that gave the best business model with these specific variables. And what ended up happening was he did exactly what we're about to do with this John shopping for baseballs and tennis balls situation, where he had to find the best scenario with his constraints. And it ends up being this double shaded region that we looked at in lesson 7. So he had to build his own two linear inequalities. He had to put them on a graph together, and then he had to look at the double shaded region and analyze that as these are the best ways to use these constraints. And what's so neat about that is he was getting his MBA, which is a master's in business association. So he was getting a higher level degree and had to use systems of linear inequalities, which I think is awesome because it's telling you guys right now that this is something applicable way later on. Okay? This is why we do this stuff is we learn how to represent different variables in different scenarios we're going to encounter and create equations that help us predict what we need in businesses, in finance, in things like that. And that's where these come into play. Okay, that's how math works, right? It's helping us to describe what's going on in the real world. And in this case, we're going to look at a simpler problem than what Thomas gave me back in those early days, right? But that's the type of thing that he was doing. So, John is shopping for baseballs and tennis balls at a sports store. Each baseball is $2 and each tennis ball is $1. He wants to buy at least 15 baseballs and tennis balls all together, but he has a budget of $20. And so this is where it comes into play is that budgeting constriction, right? So, first we have to represent baseballs and tennis balls. So that's the first thing we need to do. And we're going to use X to represent number of baseballs and Y to represent number of tennis balls. Okay. So I purposefully skipped A already because I want to come back and talk about it after the fact. Let's represent things first, then we can get into scenarios with those things. Okay. So if X represents the number of baseballs, so X equals number of baseballs. Okay. And Y represents number of tennis balls. Y equals number of tennis balls. Okay. Then what we're going to do is we're going to create two inequalities and we are going to graph those two inequalities on the system below. Okay. So I probably should have done X and Y in black, but I'm going to create two different inequalities. My first one is going to be that he wants to buy at least 15 baseballs and tennis balls all together. So that means X plus Y is something compared to 15. So he wants at least 15 total baseballs and tennis balls, right? So this X plus Y has to be greater than or equal to 15. 15 is the smallest amount of baseballs and tennis balls he can have. Now, the other issue, and I'm going to do the other one in red, is that John only has $20 to buy these baseballs and tennis balls with. So if he knows that each baseball is $2, it's 2 times X. Plus, he knows that each tennis ball is $1, it's 1 times Y, has to be less than or equal to $20 because that's the maximum amount of money he has. Okay, so we need to somehow get 15 or more baseballs and tennis balls with 20 or less dollars. That's why we do inequalities here and not just equations. I don't care where they intersect. I care where this shaded region is because there's multiple answers that will help John in this scenario. So let's graph each of these. Let's do it this way. And again, you've got only a first quadrant here. So what I'm going to do in creating this only first quadrant is I'm just going to enhance the two sides. Okay, just like this. So I'm just enhancing the two sides. So you've got an x-axis and a y-axis. Okay, so I'm just enhancing those two sides. And I want you to remember that x equals number of baseballs. Okay, and this is the x-axis. And that y equals number of tennis balls. And then this way, as you're going through, you remember what your variables are representing, even though they're in y equals mx plus b form in inequalities on your graph. So every time you're doing something with y, remember that's your number of tennis balls. Every time you're doing something with x, remember that's your number of baseballs. Okay. So let's get this in y equals mx plus b form. We'll start by subtracting x over. So I get that y is greater than or equal to negative x plus 15. So that means my y-intercept here, sorry, I scooted that over a little too far, means my y-intercept here is 15. So let's count how many we've got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We got plenty of room. So we can go by ones. Just want you to kind of remember that this guy right here, he's 0, 0. Okay, that's where your origin is. So remember that, and these are going by ones. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 up. So get that guy there. All right, get that guy up there. And then my slope is -1. So that means it's down 1 and right 1. So I did my negative move by going down. My positive move is to then go right for my bottom of my fraction. Because remember, whole numbers are a fraction over 1. So -1 might be my integer in front of my x as my slope. But it is over +1. So that's why I know I need to go this direction. I've got an x move and a y move. So what I do here, since it's equal to, I can make this solid. But what I do here is I cover all of the area that has greater than 15. So I put my pen back on the y-intercept and I count up to get greater than 15, which means all this area out here, this is the area of combinations that have more than 15 or more tennis balls and baseballs. So all this area out here is what's going to shade. All this area out here. Now, if we're on the line for this one, because it's a solid line, because there was an equal to, that would also be an acceptable, answer. Okay. So it's part of the solution set. But all that blue area, that's all the different X and Y points that have 15 or more baseballs and tennis balls. Now we need to get y equals mx plus b form for this one. And thankfully, it's the same kind of move. We're just going to subtract 2x from both sides to get 1y all by itself. So y has to be less than or equal to -2x plus 20. And we do have 20 as a y-intercept, so that does work. But now my slope is -2 over 1. So down 2 and right 1. Down 2 and right 1. Down 2 and right 1. Now remember, the whole point of inequalities, and I'm continuing to down 2 and right 1 as I talk, but the whole point of inequalities is to find the double shaded region, not the intersection point. So the intersection point is not what I'm interested in here. What I'm interested in here is where do the two shades intersect? Okay. And now here, 20 is my y-intercept, and I need y to be less than or equal to that. So down from 20 is 19, 18, 17, 16. See where the shaded region is this time? This is my shaded region, which of course creates a double shaded region of S right in here. This is where the points that satisfy both constraints lie. So any point on either line is fine because we have the equal to part. So we can spend 20 bucks. We can have only 15 baseballs and tennis balls total. Okay, though that's why those get to be equal tos. Any point inside this shaded region is also $20 or less. Excuse me, spending $20 or less. Okay. But that's what we want to look for. All right. What's one combo that John can buy that satisfies both constraints? I'm going to go with right here. There's one combo because I'm inside the double shaded region right here. This is 1, 2, 3 up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 3, 13 is one combination. Now, what does 3 stand for? It's the number of baseballs John can buy. What does 13 stand for? The number of tennis balls John can buy. And let's think about that. 3 times 2 is 6. 6 plus 13 is 19. It's $19 total that John would be spending. He'd still have another dollar in his budget. See what I'm doing there? Just double checking my answer, making sure that this adds up to more than 15 balls. 3 plus 13, we're at 16. So it's 15 or more. And making sure I'm spending $20 or less. And I spent $19 on those. Now, what we do want to look at are some maxes. Okay. What's the maximum number of baseballs that John can buy? And here's how I know what that value is. I did say we could be on the lines, right? So I'm looking this way to increase number of baseballs. And what's the furthest I get to? Well, the furthest I get to is here. That is still considered double shaded region. And that's 1, 2, 3, 4, 5. 5 baseballs is the maximum number of baseballs that we can get and still get 15 total baseballs and tennis balls. Okay. And that's because this is the furthest over the double shaded region goes. So the furthest right that the double shaded region reaches is 5, meaning 5 is the maximum number of baseballs John can buy that satisfies both, because that's the important part, is both constraints need to be satisfied. Constraints. Sure, you could go ahead and tell me that, oh, John can buy 15 baseballs, duh. But 15 times 2 is 30, and that's more than John's budget. So he can't and satisfy both constraints. You see where we're going there? So that's why you need to, with these situations, have 2 variables and 2 equations, inequalities, representing your situations that you find yourself in. And the double shaded region is where both of those are met. Okay. Pause on this for a moment if you need more time to take this in. Okay, pause on that for a moment. Make sure you understand how I built my inequalities and how I labeled my variables, then how I put them on the graphs, and how I got my shaded regions. If those pieces, the getting the shaded regions and putting them on the graphs, are still confusing, that's when you'll want to go back and do the extra lesson for the extra practice for chapter 5, lesson 7, where we did our systems and put them on the graph. You'd want to do extra practice and run it by me to make sure you were doing it correct. Okay, so can John buy 8 baseballs and 10 tennis balls? And this is why I saved this for last. This technically should have been the last question. We know from question E that 5 is the most number of baseballs John could buy and actually satisfy both constraints. So, can John buy 8 baseballs? Nope. Does this satisfy both constraints? Nope. Can't buy more than 5 baseballs and have both situations come out. So that's why I saved that for last, because we did all the work that got us to where was our max anyway. So then we can go back and talk about that particular problem. Let's try this again. Okay, there's more than just baseballs and tennis balls here. Oh, this is great. So this is part of your homework. Is all you need to do is write inequalities that model the problem. You're not going to need to solve them. Okay, because really the only way to really solve these will be to graph them, right? To see that double shaded region. So let's just label our x and y as variables and create our inequalities, okay, in these two problems, because that's part of the homework tonight, is just labeling what x and y are representing, or in this case r and d, right? And then create your inequalities. So Frank is putting together a bouquet of roses and daisies, and he wants a combination of a dozen flowers. How many is a dozen? 12. Got it. Roses cost $4 each. Daisies cost $2 each. Frank must spend $40 or less on this bouquet. R represents number of roses, and D represents number of daisies. Oops. There we go. Fixed. Okay. Now let's create two inequalities that model this. So the first inequality is going to be just a total, right? How many total flowers does Frank want in the bouquet? He wants 12, a dozen. So R plus D needs to be a dozen. Could it possibly be more than a dozen? Could it possibly be less than a dozen? It doesn't say. So this is going to be on the line, right? He wants a combination of a dozen flowers, but he needs to spend less than 40 bucks. So that's this one being an inequality, right? Roses are $4, so 4 times R, plus daisies are $2. 2 times D has to be less than or equal to $40, because it's $40 or less on the bouquet. Notice I had one equation that was just my numbers, getting a dozen flowers in the bouquet. My other equation was just my money, getting $40 or less for the bouquet to cost. That's it. I don't need to solve it. I'm done. A diet food company is attempting to create a non-carb brownie composed entirely of fat and protein. The brownie must weigh at least 10 grams but have no more than 100 calories. Fat has 9 calories per gram and protein has 4 calories per gram. X represents the weight in grams of protein and Y represents the weight in grams of fat. Write the system. Okay, so we know our constraints. So X is going to equal the weight of protein, and Y is going to equal the weight of fat. Okay, now we need to have the brownie weigh 10 grams, but no more than 100 calories. So let's start with the 10 grams, right? Because each of these weights are in grams. So X plus Y has to be less than or equal to 10 grams. Now it's per, right? So how much does fat have for calories? Well, fat has 9 calories plus protein. Wait, sorry. X is weight of protein. Oh, my bad. They gave them to me in the opposite order that I had my variables. So this should be 4 calories per protein, right? And 9 times Y gives me calories per fat, because fat is Y, right? That needs to be no more than 100. So that needs to be less than or equal to 100 total calories. That's how we would create those two. Oops, I didn't do that in a different color. I suppose that's okay. That's how we would create those two inequalities. To then, if we wanted to completely solve the problem, then we would put those on the graph. Now, these just asked us to build our inequalities, so we do not need to solve these problems. We just had to build the inequalities we would use to solve them. That's the majority of your homework, is just building the inequalities. There's only one question on your homework you're actually solving. So it's kind of nice. All right. Exercise 3. Rudy got a job at an ice cream shop for the summer. He needs to order boxes of small cups and boxes of large cups. The storeroom can hold a total, up to, got it, 10 more boxes. Oh, okay, because he's ordering more boxes. Got it. Each box of small cups costs $100. Each box of large cups costs $150, and a maximum of $1,200 is budgeted for cups. So this is another budget constraint, right? So how much does our stuff cost? We're going to write an inequality to figure this out. Again, we'll use X and Y. And again, because we're not going to be dealing with negatives, we just have a first quadrant. So I'm just going to kind of highlight my X axis and my Y axis on the edges here, just so we remember that this is a first quadrant only, because we're not going to be dealing in negative for money, nor are we going to deal with negative for cups. So I'm just highlighting my two axes so we remember that. Write a system of inequalities. Got it. So X is going to equal number of boxes of small cups. And Y is going to equal number of boxes of large cups. Okay, so that way you know what each of those two variables is representing when we go and graph them. So now let's write two inequalities. And my first inequality is just going to be how many more boxes can the storage room take? And it's 10 more is the maximum that storage room can handle. So X plus Y has to be less than or equal to 10. 10 is the maximum amount of more boxes that can fit in that storeroom. Now, if we're going with money, it's $100 per box of small cups plus $150 per box of large cups. And that actually has to be less than or equal to $1,200, because that's all that's budgeted for our cups. Okay. So now what I'm going to do is I'm going to get those in y equals mx plus b form and put them on my graph. So let me put both of them in y equals mx plus b form first, so I can make sure I'm going to have room for my y-intercepts, okay? Because this looks like, ooh, 100 and 150 and 1,200 might be too big for this to go by ones, but in reality, let's see what that looks like, okay? Because I can promise it's not quite as bad as it looks, right? So we'll start here with x plus y, and we'll subtract the x over. And so you get y is less than or equal to. negative x plus 10. So that's the first one. Here, we're going to start by subtracting the 100 over. So you get 150y is less than or equal to negative 100x plus 1200. But what you have to do to get y all by itself is divide by 150. So these numbers actually get significantly smaller. You get y is less than or equal to, well, I didn't divide by a negative, so that's good. And over here, hold on, I gotta get my mouse over. There it is. Over on this guy, let's see, we've got negative 100 divided by 150. Oh, that's gonna come out to be a fraction. Ooh, I need that in fraction form though, because I need it as a slope, right? So let's do math and see how this is, change it to a fraction. So enter, negative 2/3, got it. And then 1200 divided by 150, okay. Let's see if this comes out to be an integer, and it does. So look at that, a much more normal number situation that we're actually dealing with in this scenario. So let me start by graphing the blue. And again, remember, this is your 0, 0, right? Your X is your number of boxes of small cups. Your Y is your number of boxes of large cups. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 right here. And our slope is negative 1 over 1. So down 1 and right 1 gives me a negative slope here. There we go. Awesome. Shading, let's see. We need y to be less than or equal to. So less than 10 is 9, 8, 7, 6. So this is where we're going to shade the blue area. All right. Now let's get the red on there. That's going to have a y-intercept of 8. 1, 2, 3, 4, 5, 6, 7, 8. And a slope of negative 2 over 3. So down 2, right, 1, 2, 3. 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 Again, solid line too, right? Because we know we got equal to. We can spend $1,200. We'd like to spend less than $1,200, but that's what the budget is for cups. And y has to be less than or equal to this. So I put my pen back on the y-intercept, and less than 8 is 7, 6, 5, 4. So this is my red shaded region. And if I look at the double shade where all the answers are, it's right in here. So anything on those lines and in those double shaded regions, both things, anything in here, that will satisfy this. Okay, so state a combination of small cups and large cups Rudy would be able to purchase. So let's just pick a point inside this double shaded region. That would be 1, 2, 3, 4, 5, up 1, 2, 3. So 5, 3, which is 5 small cups and 3 large cups. That is less than 10 boxes for the storage room that can't fit more than that. And then if we do the math quick on how much money that is, 5 times $100 per box plus 3 times $150 per box ends up being less than $1,200. It's only $950. So this combo leaves space in the storage room and money in the budget. Okay. If we were trying to maximize, we would go with like this. this point right here or a point right here, right? You're maximizing the budget, right? And the storage space. Okay. All right, guys. Again, if you need to, pause it on this so you can make sure that you understand how I created my variables, how I named my variables, how I created my inequalities, how I then got y equals mx plus b form, how I then graphed each, how I then got my shaded regions, and then how I found my double shaded region. Where's the area that's shaded by both? Okay. All right. Good luck. This is the last piece of the chapter, and I shall be seeing you for the exam. Let's make sure we do some exam review together. So I'll probably do a video for that guy too. Good luck, guys, and let me know what you need before the exam. Bye.